Welcome back, everybody. We're going to continue working through 11.4 here. Areas and lengths and polar coordinates. So we want to find the area of the region that lies inside the circle, r equals 3 sine theta, and outside of the cardioid, r equals 1 plus sine theta. So again, we've got different things going on here. We want to be inside a circle, but outside a cardioid. So graphing here is essential to kind of visualize how we're going to get those areas. So let's go ahead and graph both. So let me make some space here. All right, so we've got 3 sine theta. So that is going to be a circle with radius 1.5. Since 3 is the maximum distance, that'll be the diameter. And this is going to be symmetric about theta equals pi over 2 because we have that sine theta term there. And again, these are just going to be really nice facts to use for these cases. Again, we could plot points, though, if we needed to. So theta equals pi over 2 is going, or sorry, r equals 3 sine theta is going to look like a circle with diameter 3. And then our cardioid is 1 plus sine theta. So that's going to be a cardioid that is also, like our circle, symmetric about theta equals pi over 2. So what that means is that we're going to get our heart shape. We'll note the max value here is going to equal 2. So it's going to be inside of our circle. So it is going to, actually, let me make it a little bit more exaggerated. It's going to look like that. All right. So we want to be inside the circle, outside the cardioid. So that means we don't want to be anywhere inside the cardioid, which means we want this area here. Okay. So again, now we're going to have choices, but now we also have to worry a little bit about how we are computing the area. So let's just note here. We're again going to have the choices of using symmetry or not using symmetry. So let's just note, if I look at this region in the first quadrant, right, that area is symmetric to the area on the left. So I really only need to find this area on the right and then double it. Now I could still find the whole area. And so there's going to be kind of 2 possibilities that we can choose. And what we're going to notice here is that just like area between curves for rectangular functions, we're going to be interested in those intersection points. My picture's off here. Clearly, those are going to be symmetric in some way. So why don't we start with intersection points? So intersection points are going to be something we'll be interested in. So let's put that up here. Intersection. All right, so that's going to be when is 1 plus sine theta equal to 3 sine theta. So we'll set our 2 polar curves equal to each other. We can see that we can subtract a sine theta, so we'll have 2 sine theta, so 1/2 equals sine theta. So theta is going to equal pi over 6 in the first quadrant. And then in the second quadrant, that's going to have to be 5 pi over 6. So we'll just note that coordinate is going to be, so if we have pi over 6, r is 1.5. And then this will be 1.5 and 5 pi over 6. Okay. So those values are going to be important. So the question is now how do I compute those areas? So let's kind of visualize a little bit more on what this is going to look like. So if I just look at my circle, right, maybe I think I want to start at pi over 6 and, and just go to pi over 2. So let me make a note of that point here. So 3 comma pi over 2. So that's going to be on my circle. And for my cardioid, I'm going to have the coordinates 2 comma pi over 2. All right, so let's think about how the circle is going to trace. So our circle is going to start when we're at 0, we're at 0. So we start at the pole, and then we rotate this way, as we reach that top value. So we're going to trace out that way, which means our area is going to trace out that way as well. Okay. So then if I start at pi over 6, right, because clearly I don't need this region below, then let's say we started at pi over 6, and then we trace out the rest of our circle. So that means we're going to slice it there, and then trace out that section. Okay, seems pretty good. But then I also have to take into account that I'm going to be removing that blue portion. So we kind of need to think about how that blue portion also traces out. And it's going to turn out that it's going to trace out the same way. Right, so it's going to trace out from right to left as we rotate to pi over 2, which means I can get that region by taking the area inside of the cardioid and subtracting it from that area inside of the circle. So in other words, we're going to do A1 minus A2. This is A1, and this is A2. And then again, we can double that value to get the total area on the other side as well. So that's what I'm going to use to calculate here. So let's set up our integral. So area is going to be 1/2. So I'm going to take the integral from pi over 6 to 5 pi over 6 of my circle. So that's 3 sine theta squared. And then I'm going to subtract the area of my cardioid, which is also from pi over 6 to 5 pi over 6. So it's going to be 1 plus sine theta squared d theta. But if I do that, then let's note I could have just written this as a single integral, right? Because our domains are the same. So in other words, this is really equal to 1/2 integral pi over 6 to 5 pi over 6 of both of those functions. So 3 sine theta squared will be 9 sine squared theta minus, and then 1 plus sine theta squared is going to be 1 plus 2 sine theta plus sine squared theta d theta. So now I can go from two integrals to 1. And this is going to be something that we can do quite often with this area between, but not always. We're going to have to be a little bit ingenuitive about some of our approaches. All right, so let's go ahead and evaluate this guy. So we're going to get 1/2 integral from pi over 6 to 5 pi over 6. Oh, and I made my first mistake, which is mixing up my angles. So we don't want to go from pi over 6 to 5 pi over 6 necessarily. So in this case, it actually does work because we're going to trace that way, but I didn't really mention that in my explanation. I really meant to do to 3 pi over 2 and then double. So note, it would be 2 times 1/2 integral 0 to pi over 2 of our expression. And one of the reasons for wanting to do that is that pi over 2 is going to be 0 or 1 for our sine values. We're going to have double angle measures and things like that, but for the most part, it's going to be 0 or 1, so it just becomes easier to calculate. Whereas pi over 6s can get quite messy. So let's just note that we should have done double the angle measure, but we'll note that our area traces out, simultaneously the same way on either side. Again, this won't always be the case. So if we want that area, we could do what I've written previously, which is to just integrate from from pi over 6 to 5 pi over 6. So So from pi over 6 all the way to 5 pi over 6, because those will trace out the same way. So why don't we go ahead and just keep working with that approach, and we will, and this should be pi over 6, not 0. So if you did double the area, it'd be from pi over 6 to pi over 2, and again, pi over 2 is a little bit nicer to calculate, but let's go ahead and we'll just do it from pi over 6 to 5 pi over 6. All right, so we can distribute that -1. So we'll note those are all going to change sign, which means I'm going to have a minus sine squared. So that means instead of 9 sine squared, I'm going to have 8 sine squared. And then we'll have minus 2 sine theta minus 1 d theta. All right, so let's go ahead and calculate. So we'll have, I'm going to have to simplify the sine squared as well. So we'll note this is 1/2 1 minus cosine 2 theta, which times 8 is going to become 4. So 4 times 1 minus cosine theta. So the integral of pi over 6 to 5 pi over 6 of 4 minus 4 cosine 2 theta minus 2 sine theta minus 1. We can combine the 4 and the 1 and just make that a 3. So 4 minus 1 is 3. And now we can integrate. So let's see, we'll have pi over 6 to 5 pi over 6 of 3. Oh, actually, yeah, let's just integrate. So we'll have 3 theta minus 2 sine 2 theta minus plus 2 cosine theta from pi over 6 to 5 pi over 6. All right. All right, so let's go ahead and evaluate this guy. So we've got 1/2 So we'll have 3 times 5 pi over 6, which will be 5 pi over 2. And then minus 2 sine of 5 pi over 3, which is going to be negative. So this will become 2. And then 2 rad 3 over 2 will cancel the 2's. And then 2 cosine of 5 pi over 6 is also going to be rad 3, but it'll be negative. So that's pretty nice. Those two cancel. And then at pi over 6, we'll have 3 times pi over 6, which is pi over 2, minus, so we'll have 2 rad 3 over 2, so radical 3 again, and then plus radical 3 again. So this one's going to work out really, really nicely. We get all the radicals cancel out, and then we're going to end up with 5 pi over 2 plus pi over 2 is 2 pi times 1/2. Simply gives us 1 pi. So our answer is going to be pi. Awesome. And we'll just note we can verify this on Desmos. So I calculated this a little bit earlier. So you can see that your answer is 3.14159, which is pi. And that was just subtracting between pi over 6 and 5 pi over 6. So suppose that we wanted to look at that symmetric version that I mentioned. So let's say that would be 2 times 0.5, which would just cancel. And then we would have the integral from 0 to pi over 2 of the difference of those two functions. So let's see if I can copy. Oops, no, don't want to do that. So we've got 3 sine x squared. Let's put that all in parentheses, minus, oops. then 1 plus sine theta. And now you can just use x as your variable in between, and oh, we get something a little bit different. Ooh, that's interesting. So, from pi over 6, sorry. Pi over 6 to pi over 2. There we go. All right, yeah. So we can see if we double the integral and multiply out the half, which cancels, and we integrate from pi over 6 to pi over 2, we'll get the same answer. So just note that there's multiple ways to approach each one of these. All right, so getting back to our notes then. This is really getting to what's going to be the more challenging areas to find, which is the area bounded between two polar curves. So in general, the formula is kind of written this way, but I'll just mention to be very careful. And the reason for that is that we're going to get regions where, they're non-symmetric, or we have to be very careful with our angle measures. So this is only true where both of those curves sweep the same area for the same angle measure, right? So they have to be in exactly the same location. Just note for certain curves, you could have a curve that maybe has a nice symmetric region, and it measured it out this way, let's say. But at that same moment, your other curve might look a little bit different, meaning it's not in the same location, not sweeping out the same area. So the way that you sketch the curve and think about how it's sweeping across those two angle measures is going to be very, very important. All right, so let's go ahead and jump right into some examples here. So now we're going to take the same scenario we were just in. So we had the circle and cardioid. And note, same circle, same cardioid, so we still have pi over 6 and 5 pi over 6 being our intersection points. But now we want the area that is outside of the circle and inside of the cardioid. So we want no area in the circle, but we want any region that is inside of the cardioid, which means that what we're looking for are these two regions down here, because the rest of our cardioid is inside of the circle. So we want those two regions, and we'll note that those are two separated regions, right? Those two regions are completely separated from each other angularly, unless we start on the left, right? So we could think of maybe sweeping out this way, which means we're going to start with a angle measure on the left, which is, in the second quadrant, sweeping to the first quadrant. So this is going to take a little bit of different approach, possibly. What we'll note, though, is that both regions are symmetric. So we're going to want to use symmetry here, because then that means I only need to find one of those regions, and then I'm good to go. So let's just note, we want to calculate our area as 2 times the integral of whatever that region is that we're sweeping out. So let's go ahead and now get into kind of thinking about how we're going to achieve that. Now for the cardioid, it seems pretty obvious that we want to sketch our curve like this, right? So it means I want to start from below and then sweep to the right and upward. So that actually works. But then that means that I'm not starting at 0 radians. I'm not starting at standard position. I'm starting at when my curve is 0, and in the fourth quadrant. So that means that I'm starting in reverse of 0. So the angle measure I'm going to begin at is going to be negative pi over 2. Right, so because I still want to sweep through 0 degrees, obviously. So 0 degrees, I still want to, still want to sweep from 0 degrees and up, but I can start in reverse. I can start before 0, technically. But I don't want to use 3 pi over 2, because then I'd have to do 3 pi over 2 to some angle bigger than 2 pi. So if we're going to start below the axis in the fourth quadrant, or if we started in the third quadrant, we'll want to use negative angle measures, typically, that are going to be smaller than 0, but that are going to be manageable values. Okay, so that means we're going to start at pi over 2 and sweep all the way up till we get to pi over 6. So that means that our cardioid region integral area is going to be from negative pi over 2 to pi over 6. But what we'll notice, though, is if I do that, there's still a chunk of the circle there, right? So there's going to be a chunk of the circle that's represented because I'm cutting a straight line to the origin from pi over 6. So that means I need to remove that small little chunk of the circle, but that small little chunk of the circle is still from 0 to pi over 6. So in order to get that region that is cardioid only, I need to take the cardioid region that sweeps minus that little overlap region that is going to be the circle. So this little overlap region down here. And here's where it gets tricky, because you'll notice these are different domains, right? These are not equal to each other, which means instead of just doing the integral from a to b, as area between suggests, we're actually going to have to write 2 separate integrals. So let's just make note of that we're going to have 2 separate integrals. We're going to have the area of our cardioid minus the area of our circle. So again, this is going to be kind of typical where you can't just necessarily do like an exact overlap, because you've got these regions that are sweeping from different angles. So in this case, from negative pi over 2 to pi over 6 for that cardioid region, and then from 0 to pi over 6 for that circle region that is inside of the cardioid. All right, so let's go ahead and we'll note that the 2 still multiplies. So we're going to cancel the halves out with the 2's. And now we just need to add both of those integrals. All right, so 1 plus sine theta is going to be 1 plus 2 sine theta plus sine squared, which again is going to be 1/2 times 1 minus cosine 2 theta. So we'll just note that's what that's going to look like, which is going to give us, when we add it to the 1, so negative pi over 2 to pi over 6. So the 1 and the 1/2 combined to become 3/2. And then we'll have plus 2 sine theta minus 1/2 cosine 2 theta d theta. And then the integral from 0 to pi over 6 is going to be 9 sine squared. So it'll be 9 times 1/2 of 1 minus cosine 2 theta. So that's going to become 9/2, which I can just factor out. And then we'll have 1 minus cosine 2 theta d theta. All right. Yep. and now we can evaluate. So again, these will get messy, as this one looks like it's going to. And then we've got plus minus 2 cosine theta, and then minus 1/4 sine 2 theta. All evaluated from negative pi over 2 to pi over 6, and then minus 9/2, and then theta minus 1/2 sine 2 theta from 0 to pi over 6. All right, so let's go ahead and definitely be careful here. So let's zoom in a bit on this integral. So at pi over 6, we'll have 3 pi over 12, which is pi over 4, minus, that looks like it's going to be radical 3, minus pi over 6 is pi over 3, so that's going to be radical 3 over 8. Yes. Minus, and then at negative pi over 2, so we'll have negative 3 pi over 4. And then cosine of negative pi over 2 is the same as cosine of pi over 2, so that's just 0. And then sine of 2 pi will just be 0 as well. All right, so that's going to be our first integral. And then we'll subtract from that 9 over 2, and then pi over 6 minus 1/2, so that's going to be sine of pi over 3, which is rad 3 over 4, and then minus 0. So that'll just be that. All right, so let's see what we end up with. So let's just look at terms here. So that's going to be positive 4 pi over 4, so just pi. And then I guess we could make this 8 rad 3 over 8, so it'll be minus 9 rad 3 over 8. And then we'll subtract, so 9 times pi over 6 is going to become 3 pi over 4. And then plus 9/2 multiplied into, we'll get 9 rad 3 over 8. Oh, look at that. That works out so nicely. All right, so we get cancellation there. And then we get pi minus 3 pi over 4. So that gives us an area of pi over 4. All right. So quite the messy integral, works out pretty nicely. So this is an example of kind of a longish non-calculator problem, but this could also be a calculator problem, obviously. And for the examples where it's really kind of very specific domains, so these domains that don't overlap, most of these on the AP will probably be calculator style questions, whereas the more straightforward calculations on the same domain would be a non-calculator question. All right. So that's, again, our first area between curves kind of officially, although the one we did on the previous video is also an area between two curves in the more straightforward sense. All right, so that's going to conclude the notes. So if you have any questions, shoot me an email or come by the office hours. Otherwise, until I see you next time.